Hello, this is a lecture for my Sem 4 student of quantum mechanics. We had been recently studying the postulates of the quantum mechanics, and as you know, we had already studied the first two postulate. The first postulate is actually the representation of the states. If we talk about the postulates of quantum mechanics, then I can say that the first postulate is the representation of the states, which actually define a wave function psi. Second postulate was about the fact as the observable, so physically observable quantities, those can be represented in terms of Hermitian operators, observables as Hermitian operators, and I have shown you, I have given certain materials also, written materials, which proves that Hermitian operators actually give us real eigenvalues, and if a Hermitian operator have simultaneous eigenfunction with different eigenvalues, then the eigenfunctions would be orthogonal to each other. This much we have studied till now. We would go further. In this particular lecture, I would first of all like to give you an idea about the type of the Hermitian operators for different physical quantities. There are very many physical quantities which can be expressed as their corresponding operators, and we would like to assign each of them with a particular mathematical operator. For example, if you talk about the position operators, position x, y, z, then the corresponding Hermitian operator in the configuration space are given by operators given as x cap, y cap, z cap. So the potential, which is a function of x, y, z, would be potential in itself, which is a function of x cap, y cap, z cap. The momentum operator p, which can be written in this particular case as minus of ih cross del del x, if this is a px. Okay, so px, py, pz, the linear momentum operators can be written as minus of ih plus del del y. These are all in a configuration space. And if you talk about a vector p, then that can be written as minus of ih cross del. Okay. Then there are these are the components of the linear momentum, and this is the vector form. So linear momentum. So one can even express the corresponding energy operator. Energy operator can be written as ih cross del del t. Okay, and Hamiltonian kinetic energy operator can be written as minus of h cross square by 2m del square corresponding to p square by 2m. Okay, this is equivalent to p square by 2m. Okay, potential energy is V, so the Hamiltonian can be written as the kinetic energy and the potential energy, which is minus of h cross square by 2m rad square plus V, which is again an operator, V operator. So there, then one can express the angular momentum operators, So if one talks about the Lx, Ly and Lz, or L is equal to R cross P, then that can also be written as minus of IH cross R cross del. This is the angular momentum operator, components of L. So Lx, which is equal to y pz minus z py, can be written as minus of IH cross y del z minus z del y. In the same fashion, other components can also be written as z px minus x pz, which is equal to minus of IH cross z del x minus x del z. And if one wants to write Lz, which is equal to x py minus y px, then that can also be written as minus of IH cross x del y minus y del x. So these are few of the representation of the operators which correspond to the physical variable in quantum mechanics according to postulate 2. Now let us jump on to the postulate number 3, which says that postulate 3, which is all about the expectation value. It is nothing but the value corresponding to a particular physical quantity. Suppose we want to calculate the expectation value of what is the statistical average value of a particular operator operating on psi, which can give you an eigenvalue of A. For example, we have an operator A which correspond to a physical variable A, small a, psi. So the eigenvalue equation is given by this, and we want to ask that what is the statistical mean value or the expectation value for this operator A. Then according to this postulate, the average value is given by the statistical definition, which is nothing but psi star A cap psi d tau, if tau be the elementary volume, d tau be the elementary volume, psi star psi d tau. So that is nothing but equal to A, because A operating on psi is going to give you A of psi star psi d tau divided by psi star psi d tau, which is equal to A. So this is the statistical average value, mean value, or the expectation value corresponding to the operator A, which correspond to a particular physical variable. The postulate number 4, it is basically all about the completeness of the wave function and eigenvalue equation. Completeness and eigenvalue equation. So suppose we have a particular state psi n, which actually represent the quantum mechanical state at a particular value of n, and we have an operator A operating on that, which gives us an eigenvalue A n psi n. Then we can always say that this set of psi n, it would form a complete set like the one which we have discussed in our previous lecture. Suppose you have a particle oscillating to and fro in a pipe, and then you can subdivide the pipe into a large number of intervals, and for each interval you define a matrix, and then you can write your wave function as a linear combination of all those matrices. For the first two subinterval you write it as linear combination of first two matrices. For n you have to write it. So those n set of matrices which were called the basis vectors, they actually forms a complete set. Complete set means it actually represents that it actually states a particular fact, as we had already studied in our vector calculus, that any particular state can be represented as a linear combination of this complete set of basis vectors. Like we had in three-dimensional vector space, we can write any vector in terms of I cap, j cap and k cap. In the same fashion, all this psi n would form a complete set, and any state of the system can be represented as a linear combination of this. So psi n actually forms a complete set. This is complete set of eigenvectors for the above eigenvalue equation. The final postulate, which is the postulate number 5, can be called as the time evolution of the state. It can be called as mentioned in your syllabus, as time evolution of state. Okay, I can call this as time evolution of states. How can one really observe the change in the physical state or the quantum mechanical state of the system with time? For that, we need to consider the relation between the energy and momentum. Let us start with a very simple case. For example, for a free particle, if we say that for a free particle we have the energy to be given as p square by 2m, and if you remember that we have written the wave function psi to be something like a e to the power I of kx minus omega t. Let's say we have a one-dimensional wave function like this, psi is a function of x. Then by using the de Broglie hypothesis, k is equal to p by h cross, and this is de Broglie hypothesis, and omega to be e by h cross, this is Planck's law. Okay, then we can always write this wave function as a e to the power I of p x minus et by h cross. Okay, and now if we want to say that this wave function must satisfy this equation, then the left hand side is having e, so we need to have on the left hand side a single derivative with respect to time, and then we must have a double derivative with respect to space. So if we now want to satisfy this particular equation for free particle, then on the left hand side there is an energy term and E term, and on the right hand side there is a p square term. And if we want to build up a wave equation which must be something which is independent of space and time, because we know from the wave equation that any wave equation, normal wave equation which we have studied till now, the left hand side and the right hand side ratio is equal to 1 by c square or c square, where c is the speed of the wave, and that is something which remains constant all throughout in the same fashion. But the difference in between a normal wave equation and the wave equation which we are going to develop over here is only that there the relation between omega and k, the angular frequency and the wave number, was a linear one, because omega square by k square is equal to constant, which was equal to c square. But here we are going to see a different dispersion relation, the omega k relation, because on the left hand side, according to Planck's law, E is h cross omega, and on the right hand side, P is equal to h cross k according to the de Broglie hypothesis. So this is something where you have a omega k square relation. So it is something which is quadratic, in a quadratic dispersion relation. Omega varies as k square. So that is the difference between a matter wave equation and a normal wave equation. Mathematically, we would try to build a kind of mathematical framework which leads to a wave equation, okay, for the matter waves. That is what we would. That is the basic goal of this postulate 5, which represents the time evolution of the state. So let us see how to do that. So on the left hand side we need to have E. So we take first derivative of psi with respect to time, because that would lead us to E. So with respect to time gives us minus of I E by h cross into psi, okay. And on the right hand side we have a p square, so we need to take a double derivative with respect to space. So del 2 psi del x square, and this is going to give us minus of p square, because there is a I, so I square gives us p square by h cross square psi. So if we want to relate these two such that in this particular equation using this, so from here we can have E to be equal to I h cross del psi del t, okay, and p square to be equal to, from here we can write E psi. Then similarly p square psi is going to give us minus of h cross square del 2 psi del x square, okay. So if we now correlate these two equations with this one, then we can easily write the left hand side to be equal to I h cross del psi del t, and this is to be equal to minus of h cross square by 2m del 2 psi del x square. This is the Schrodinger equation for a free particle, and for a particle in a potential Vx. So in that case the corresponding energy is given by p square by 2m plus v. Then the corresponding wave equation becomes IH cross del psi del t is equal to minus of h cross square by 2m del 2 psi del x square plus v psi. This is sometimes the right hand side can be written as h operator operating on psi, and this particular equation is called Schrodinger equation, which actually gives us the time evolution of the wave function. It may look like, it may appear to you that I have derived the Schrodinger equation, but this is not the case. I haven't derived the Schrodinger equation. This is to be emphasized that this is one of the fundamental equations Schrodinger equation, which is basically this is one of the, let me tell you that this is one of the postulate of the quantum mechanics, and this is one of the fundamental rule of nature. One cannot derive the fundamental postulate or the rule of the nature, but I have kind of done some kind of mathematical jugglery to really make it feasible. Otherwise it would have seemed, you would have felt that it is very difficult to understand this Schrodinger equation. So that's why I did all this mathematics to arrive. It's not a derivation, it just we arrive at the fundamental law, which is known as the Schrodinger equation. This gives us the wave equation for material particles, matter waves. This is also called the wave equation, Schrodinger wave equation for matter waves, which actually can be solved to find the time evolution of the states. Thank you.